Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is video 39 and we are in lecture 18, part C. We're going to do some more examples of hypothesis tests for the mean. Now last time we did an example and we used n equals 40, and we said that we had S, not sigma. And so now we're going to look at the exact same problem, except we're changing n to 25. So we're pretending like we had a sample of only 25 and it gave us the same values. And we want to see, just go through this example and see how things change when we do that. So part A is test at the 5% level. That means that alpha equals 0.05. Whether the new setup decreases the mean assembly time below the current value, or just decreases the assembly time is all we have to really say. Okay. Hypothesis statement. The null hypothesis always has an equals sign, and we want to know the current state or the previous state, and that is mu is equal to 18.2. And it says that we want to know if the new setup decreases, that's less than. So we'd have mu less than 18.2. So these values are always the same. This is always an equal sign. This is never an equal sign. It's always less than, greater than, or not equal to for the alternative. Okay? And then alpha is equal to 0.05. So when you're writing a hypothesis statement, this is what you need to write. Okay? Now the test statistic, again, you don't have to write hypothesis statement. You don't have to write these words over here. You can, but you don't have to. But then you put your test statistic and you say T observed. Because I have S, I have to use T. So S and T go together, right? In the alphabet, S and T go together. There's S, then T. In statistics, S and T go together. If you have S instead of sigma, then you have to use T. Okay? If you have sigma, then not so easy is Z. So I can't make a fun thing with that one. All right. So our test statistic is going to be exactly the same, except we have S instead of sigma here in the denominator. Now, because we have T, we have to do a degrees of freedom. That's n minus 1. That's going to be 25 minus 1, or 24. Okay? And we're going to plug in to T observed with the values. That's going to be the square root of 25, because n is 25. X bar is still 17.4. And mu is 18.2. That comes from right here in our null hypothesis. And then we're dividing by S, which we said was 2.1. And so when I calculate this out, square root of 25 is 5 times parentheses 17.4 minus 18.2. Close parentheses divided by 2.1 gives me negative 1.9047, etc., which to 3 decimal places is negative 1.905. Okay? And why am I rounding to 3 decimal places? Because the T table has 3 decimal places. That's the only reason here. Okay, so the rejection criteria or critical region or rejection region, it's reject H naught if, because we have a less than sign here in our alternative hypothesis, we're going to have a less than in our rejection criteria. It's going to be T observed is less than negative T naught. Now to find T naught is always a positive number, and because it's a one-sided, we need a one-sided test. We need the probability that T is greater than T naught is equal to alpha, which is 0.05. Okay? And so we need T of alpha, or T of 0.05. So we go to our T table, and we want to find the alpha, or the subscript, is 0.05. So we look down that until we get to 24 degrees of freedom. And so that is right here. So 1.711 is T naught. So this is equal to 1.711. And our rejection region is if the T observed, which was negative 1.905, is less than negative T naught, which is 1.711. This is a true statement. And if this is a true statement, then we are in the rejection region, or we have met or satisfied the rejection criteria. So our decision is to reject H naught. Now the conclusion, since we did reject H naught, there does exist sufficient evidence to support the claim that a new production setup decreases the mean assembly time of a certain item. At A, C is always 1 minus alpha, so 95% confidence level, using a random sample of n equals 24, and this would be assemblies, not setups. Okay, so we assembled 25, not 24. That was degrees of freedom. So n equals 25 assemblies. All right, so what's the p-value of this test? Well, with the t-table, the p-value, we can only find a range for the p-value, unlike the z-table where we can find the actual value. So what we're going to do is we want the p-value is going to be the probability that t is less than t observed. We're using the less than because, again, H1 was that mu was less than 18.2. And because we have a less than here, we'll use a less than here. And so this is the probability that t is less than negative 1.905. Let's go to our t-table. Remember that our degrees of freedom, which is n minus 1, is 24 in this case. So we go to the t-table, and we want n equals 24, or degrees of freedom, sorry, is 24. And these are all positive numbers, so we'll have to use the positive value in our test statistics. So it'll be 1.905. And it's between these two numbers. And since it's a one-sided test, we can just read off the p-value is going to be between this number and this number. Always remember to put the smaller number first when you're doing this. So 0.025 is smaller than 0.050. Okay? So the p-value, the best we can do is that the p-value is between 0.025 and 0.050. So with the t-table, all we can get is a range. Now let's do the same example. We're going to keep n equals 25, but now we're going to say that we have sigma. So this is a case that doesn't often happen in real life, but it could. And let's see, I need to change this. This is not a square here. There's a square there. All right, so it's 2.1 squared. Sigma was 2.1, so the variance is that squared. We have the exact same hypothesis statement. Now, instead of having t observed, we have z observed. But notice that only thing that changed is the symbol here. If the values don't change, we get exactly the same value. But now with a z table, we round to 2 decimal places, not 1. So we go to the 3rd decimal place, and it's a 4, so we round down. So the rejection region is reject H naught if z observed is less than negative z0. Now z0 is going to be the same as z sub alpha. Alpha is 0.05, so that means that the probability that z is greater than z naught is equal to 0.05. And so we look at 0.05, and we come over to our z table, and we're looking for 0.05, and we're not going to find that exactly here. We're going to find 0.0495 and 0.0505. But it's smack dab in the middle, so we can use halfway. So this is 1.6, this is 4, this is 5, so use halfway, or 1.645. Another way to get that number is to come up here and to look at, remember we wanted z sub alpha, so that's here, and we have alpha is 0.05, and so where these intersect is 1.645. So that gives you the exact value. So z naught is 1.645. So we plug that in. There's a less than negative 1.645. Z observed is negative 1.90. Yeah. This is a true statement because 900 if I put another 0 there, or the 5, whichever, this is a true statement. Therefore, we do reject H naught. If it's true, we reject. If it's not true, we do not reject. Since we reject, there does exist sufficient evidence to support the claim that the mean assembly time of a certain item, I should say, the new setup. See, I'll just come up here and see what it says. Yeah, the new setup decreases the mean assembly time. Sorry. The new setup decreases the mean assembly time of a certain item at a 1 minus alpha, so 95% confidence level using a random sample of n equals 25. These were assemblies, not setups. We want to find the p-value. Since we're using z, this is a little bit easier. So our z observed was negative 1.90. Since it's a one-sided test or a one-tailed test, we need this, and that will be the p-value. So we go to our table and look up the less than for the negative, which is the same as the greater than of the positive. See, so here we have that this is alpha and this is z sub alpha. Well, if I go over here to the negative of this and say negative z sub alpha, then by symmetry, this will also be alpha. Okay? And so if I can look up the positive of the 1.90, and that positive is right here, 0.0287. Get rid of all my other scribbling. 0.0287. This is 0.0287. And because it's a one-sided test, that is the answer. The p-value equals 0.0287. Okay. Example 4 is the same as example 1, except now we go back to n equals 40, but instead of saying that we have sigma, we're going to say that we have s. Okay. I'm sorry, we're going to say that we have, s. So since we have n greater than 30, we can still use z because of the central limit theorem. And the only thing that changed here is we changed from 25 to 40. So this value changed, and when we calculate, we get this number, which is rounded to 2 decimal places of negative 2.41. That gives us our test statistic. So we're still going to reject H naught if z observed is less than negative z naught. But negative z naught, this is still a one-sided test, so z naught is going to be z sub alpha in this case, because we have just a one-sided or one-tailed test. And alpha, we said, was 0.05. So in order to get this, we go to our normal table. Again, we can just use this this little sub-table down here for z sub alpha, or alpha over 2. Alpha is 0.05, and we said we want z sub alpha, and so that gives us 1.645. So as long as we have the probability in this table, we can use it. So 1.645 is my critical value there. So this is 1.645. My rejection region, though, is z observed is less than negative z of alpha. Z observed was negative 2.41. I have a less than sign, so I put that. I have a negative, so I put that. And then I have z naught, which I said was 1.645. This is a true statement. Since it's true, we do reject, so we reject H naught. There does exist sufficient evidence to support the claim that the new production setup will decrease the mean assembly time of a certain item at a 95% confidence level using a random sample of n equals 40 assemblies. All right, so that is the last of the cases. Now, what if instead of using less than, we said that we wanted to go to an alternate of not equal to. Now, this is more stringent, okay? It's harder to reject the null when we use a two-sided test. When we say we don't care if it's greater or less, just different from. We just care if it's significantly different. So what's the new rejection region? So the new rejection region can be written as z observed, absolute value of z observed is greater than z naught. But here z naught is equal to z sub alpha over 2 because it's a two-sided test. So we don't care if the value is a lot bigger or a lot smaller than mu. We just want to know that it's different. So here would be z sub alpha over 2, and here would be negative z sub alpha over 2. So when we add up this area, alpha over 2, and this area, alpha over 2, it adds up to alpha. Okay. So our rejection region is we don't care if z is positive or negative. We just take the absolute value. We just care about how far away from 0 it is, and that's what the absolute value is. It's a distance from 0. So the distance from 0 is greater than z sub alpha over 2. Okay? And this is going to be z of 0.025, and so z of alpha over 2, we can come over here and see what this value is. Instead of using z sub alpha for 0.05, we'd use the alpha over 2. It becomes 1.96. So this is going to be 1.96. So now you only reject if the absolute value is greater than 1.96. The new decision, well, we had 2.41. It was negative. So the absolute value of that is 2.41, greater than 1.96. Greater than 1.96, that is true. So our new decision is still reject the null. Now, if you go back to examples 2 and 3, you will not reject the null. So where we had n equals 25, our test statistic was only 1.90. So it's not greater than 1.96 here. And so we would not reject the null if we did a two-sided test here. Okay? But for this one with n equals 40, we do. So how does the p-value change from part A? So if we go from a one-sided or one-tailed test to a two-sided or two-tailed test, we need to multiply the probability, the p-value, by 2. So the new p-value is going to equal 2 times, and what did we say it was up here? 0.0287. 0.0287. So that's going to be 0.0574. So is that right? So we went from negative 2.41. Right. The p-value changes. So did I do something? Oh, yeah, 2.41, normal distribution, 2.41, 0.0080. Okay, so I this was a different, I didn't get the p-value for this one. So I was looking at n equals 25 up there. Okay, so the rejection has to be the same. So we didn't get the p-value for example 4 here, so we need to. So the p-value, maybe we'll call this C. So B is the p-value for this, and it's going to be, for our original problem, less than, since we have a less than here. So we're going to have the p-value is equal to 0.0080, okay? Because it's the probability that Z is less than Z observed. And Z observed was 2.41, and when we, whoops, wrong thing. And when we look at 2.41 in the Z table, we find that that's 0.0080. Again, we're looking at the greater than, which is the same thing as the less than of the negative. Okay, so 0.0080. And so I'm multiplying this by 2. So I'm multiplying the 0.0080 by 2, which is 0.0160. That's still less than alpha. 0.06160 is less than 0.05. That's true. That's how I knew I made a mistake, because if I say I reject H naught using one method, I have to reject H naught using the other method too. So reject H naught. So the same decision, regardless of which method I use. So, all right. So now so this is going from a one-sided to a two-sided test, we double the p-value because we have to multiply by 2. But if we're going in the other direction, then we would divide by 2. Whatever we had here, we would divide by 2 to go backwards, right? Okay, so just if that question's asked, make sure you know which way it's going. All right. If you have questions, by all means, come to virtual office hours. If you need help prior to virtual office hours, then email me, but make sure you email me a picture of the problem and a picture of your work so far so I can help you. I don't have the problems memorized, so you need to send me a picture of the problem so I know what it is. And seeing how you're approaching the problem will help me explain better to you. All right? Please take care of yourself, stay safe, because we hope to see you next time.